Okay, hello Year 13. We are going to go through your mock paper now. So I'm not going to go through the multiple choice, so I'm going to skip all of that and let's have a look at the first question. Right, that was smooth. Okay, so this is a track for toy cars and a circular loop, so it's circular motion. What we're looking at here is what is the minimum speed of the toy car at the top of the loop if it makes the loop. So let's have a look at what's going on here. It's circular motion. If we think to ourselves something moving in a vertical loop, there's always going to be centripetal force towards the centre. That's going to be provided by the other forces that are there. So when it's at the top, the centripetal force needs to be acting down, and that's going to be provided by, so here we have Fc as the centripetal force. That's going to be provided by the weight and the reaction force. Now the reaction force is going to get less and less as it goes slower and slower, and we're looking for the critical speed where it just makes the loop. So the instance we're looking at, this is going to be equal to 0. So basically Fc is going to equal mg at this critical speed. So I think the thing that people missed out here was the direction the forces were acting. So that's the bit you've got to get your head round. Once you've got that, it suddenly becomes pretty easy. So the way I would do this, I would say that at the minimum speed, what's going to happen, the reaction force, Fr, is going to equal 0. So that means that the centripetal force at the top there is going to equal the weight. And if we just substitute the equations we know in, everything just comes out. So we've got mv squared over r equals mg. Cancel the m's, and we've got what it gives you in the equation, that v equals root gr. And you can do the algebra if you want. Okay, so let's go and have a look at the next question. Okay, so for this next question, where most people went wrong is they tried to use Suvat equations. You can't use Suvat equations if it's not going in a straight line. It's rectilinear motion for Suvat equations. Also, it assumes that acceleration is constant, but it's not constant here because the acceleration keeps changing direction. It's always towards the centre of the circle. So, thing to remember, if it's moving in a circle, you can't use Suvat. But you can always use energy. And that's what we're going to do here. We're going to use conservation of energy to work out how fast it's going. And I can't write now. There we go, energy. Just to emphasise it. Okay, so if you want to know how fast it's going at the bottom of the loop, it's going to have kinetic energy at the bottom of the loop. So the kinetic energy at the bottom is going to equal, well, if it's going round the loop, it has to have some kinetic energy at the top. So it's going to equal Ek at the top plus the fact that it's higher up, so plus the potential energy at the top. And then you solve for this, and it comes out quite easy. So we've got half mv squared here is going to equal half mv squared at the top plus mgh. But we know at this critical speed, if it says without losing contact at the top. So it's talking about the thing from earlier on in the question. We know that this v here is going to equal root gr, which means that v squared is just going to be gr. You substitute all that in, cancel the m's, and you end up with v squared equals root gr. What am I on about? Just equals gr. Equals gr plus mgh, but the m's have cancelled, so plus g times h. And it comes out at the end at 2.7 meters per second. But you can work through that one yourselves. Next one was pretty straightforward. I think it was pretty, well, you seem to think it was pretty straightforward. Most of you got this one okay. Those of you that made a mistake here, you mixed up horizontal and vertical components. So the idea is you work out, well, first of all, the time it's in the air. And that's basically the time for something to drop with an initial velocity, initial vertical velocity of 0, with an acceleration of minus 9.81, and the displacement, it's falling 0.65 meters. So just for consistency, if I've set the acceleration negative, I'm going to set the displacement as minus 0.65. I would use s equals ut plus half at squared. U is 0, so that just rearranges to the time it takes to the fall is root 2s over a. It's worth learning this one off by heart. Comes in handy. Basically it's the equation you're using in the g by freefall experiment as well. Now you know how long it's in the air, and you knew the horizontal velocity at the start was 3 meters per second. You can just use distance is speed times time, because the horizontal motion is not accelerated. So you can use s equals ut, and I think it comes out at 1.1 meters. But you can do that calculation. Okay, so that was question 1.